Hi everyone. In the previous class, we have seen the concept of how to simplify Boolean functions, right? So means basically we can do solving of a Boolean function using Boolean theorems, or we can say that postulates, right? The another way, that is what we have seen in the previous class, is KML. This is the simplest way to solve it, right? Because there are some drawbacks we are going to face when we are trying to solve with respect to Boolean theorems. Like we may get more than one kind of solution, or it is difficult to solve it to a minimized expression like that, right? To overcome these drawbacks, we are moving for K-maps, right? So in K-maps, basically, we are going to form a subcube which is of size 2 power m. If it is of size 2 power m, we will get n minus m variables in a particular term, right? Where n means what? Number of variables. Okay, fine. So here, uh, when you're trying to do this particular procedure, we may get certain kind of redundant terminologies also, redundant terms, right? So meaning that, for example, if you try to take a three variable k map where your min terms will look like this, right? At this situation, you are going to take this as one uh, implicant and this as one implicant, and sometimes you may take this also one implicant, right? So if you are able to clearly observe, this is a kind of redundant term. So that's the reason. So you have to follow certain procedure to avoid this kind of redundant terminals, right? So this is where we are trying to know the point called prime implicants and essential prime implicants also, right? And so to make our solution very efficient, we have gone through some procedure. I have taken a best example how to solve it also, right? Then we have seen the equivalence between two functions, right? If I am going to have two functions f and g, is f is covering g or g is covering f, or both covers itself, right? When both are trying to cover itself, then I can call it as both functions are equivalents. And also we have seen the don't care terms, and also we have seen one more kind of important concept, variable entrant map. Along with this, we have seen the previous kind of gate questions, guys, right? But the thing is, when you are trying to discuss the gate questions, as uh, we are at the end of the classes, like it's almost 3 hours, right? So when we are trying to do this, we made some mistakes here. So if you are able to observe this question, which function does not implement the Karnaugh map given below? See, I am trying to add the question, right? Guys, if you are able to observe this one, if you are able to observe, right here, uh, we need to find the function which is not implementing with this K-map, right? So what you can do, guys, here, basically they have given in the form of sum of the products as well as product of the sums, right? So first try to find out for sum of the product, right? If you would like to find out the sum of the products expression, so you need to take out subcube of size 2. So I think it is 2 power 2. So I can say that it is basically an xy term, right? Similarly, if you are going to combine this one, you are going to get y is not changing, so you will get y, and from the x-axis you are going to get w is not changing, so yw, right? So this is what, right? So if you are going to take this xy plus yw, so this is going to be generating, but they are asking for which is not implementing, right? If you are going to take out the common for this one as y, you are going to get x plus w, right? Which is same as w plus x into y. So this is also going to be generated, right? Now try to check the case for option c. Option c, right? Option c is in the form of product of the sums, right? when it is in the product of the sums, so your equation will be like this kind of expression, right? So you need to find a situation where you make it this kind of thing or not, right? So I will try to do that. I will try to select the max terms in such a way that, can I select these four as one term? Yes, right? So basically here what is changing? This 0 and 1 is changing, 0 is not changing. So 0 means what here? It should be y, it should be y. And between these two, which is changing? Only w is not changing. So I can say that y plus 1 means what? W bar. W bar. Okay. So I think we covered this one. We tried to cover this one. Y plus W bar. Right. And can we do some kind of thing where can we able to do this particular thing? Yes. Right. So if you are going to do this one, you will get uh, x is not changing. So you are going to get x, and among the x-axis you are going to get z is changing, so w is not changing. I can say that w plus x. So this is also covering. And if you try to observe this one, right? So here between these two, x is changing, y is not changing. So I can say that y plus, on x-axis again it will be like z is changing, w is not changing. So if you observe, uh, w is not changing, w is not changing, right? When w is not changing, I can say that it will be w. And on x-axis, see, you need to cover this term compulsory, right? You need to cover this term compulsory. So to make this term compulsory, so try to observe what I did. Initially I tried to cover this term. Okay, now we are trying to cover the first and last, right? When we're trying to cover the first and last, x is changing actually, y is not changing, so y we got. And on the x-axis side, on both terms here, uh, try to observe, z is changing, w is not changing. So I can say that y plus w, when y plus w is there, no. Is there any chance to get x bar plus y? We can do something like this to get this answer, x bar plus y. Can I do like this to cover this one? Yes. So for this the answer will be x bar plus y. So option C also possible. So the correct answer for the given question is option D. I hope you understood now, right? So you have to select the Karnaugh map based on the options also. Okay, fine. And if you look into one more example, like this one, right? Here also we did a mistake. I will try to add the question. Uh, this is the question they have given. Okay, fine. So here in the Karnaugh map shown below, x denotes a don't care term. What is the minimum form of the function represented by the Karnaugh map? So what you can do guys here? So earlier we try to do something, so we got the wrong answer. Now try to do again selecting the min terms, right? So when you are trying to select the min terms, uh, try to select the possible action, right? So earlier what we did now, we selected this one directly. That's the reason we got mistake. See, actually it is correct, but we need to cover the correct way, right? Because when you are trying to cover this way, you are going to get extra term also. So that's the reason. Instead of like this, can we able to do like this? Yes. So for this, if you are able to solve, you are going to get, I think C is going to be changed, so D is not changing. So you'll get D bar. On the x-axis, A is not changing, so you are going to get A bar, A bar. Right? Now, if you are able to solve this one, right, it will be, I think, around corners to cover that, right? If it is around the corners, so I think A is not, A is changing, so B bar you are going to get on the x-axis, and on the y-axis C is changing, so D is not changing, so you are going to get D bar, right? Finally, the expression will be like this: A bar D bar plus B bar D bar. So option A is the correct answer. Okay. So when you are trying to solve this kind of questions, you have to be careful. Okay, fine. Now, in today's class, in today's class, we'll see another concept, that is combinational circuit. See, so far whatever the circuits that we have drawn, all will becomes under combination circuits only. So means these combination circuits are going to produce the output by taking present input. I mean, for example, if you are trying to take a simple calculator, a basic calculator, this calculator, for this you are going to give inputs as 5 is one button and 7 as one button, and you are going to produce a result as 535, right? Similarly, when for the next iteration, if you are going to give some number like 6 and 8, 6 and 8, again you are trying to perform the multiplication operator, you are going to get 48 only, right? Meaning that this output 48 is depend upon the present inputs only. That kind of circuits I can call it as combinational circuits. Okay, meaning that it won't think about the past, it won't think about the past. Whereas coming to another kind of circuits are there, those are sequential circuits. Sequential circuit, right? They are going to follow sequence, meaning that they are going to think about, before going to produce output, they are going to compulsory think about present input as well as previous history. These two will yield to the present output. Okay, I mean, if you try to take one assumption as a kind of a circuit, so I will call it as a combination circuit. For this combination circuit, I am going to give n inputs right now. For these n inputs, it is going to produce the respective outputs. I can say that m outputs it is going to be produced. Okay, whereas coming to sequential circuit, it is also going to produce m outputs, and it is going to take n inputs, but this output is not only depend upon these inputs, but also it is going to depend on the previous history. Meaning that I can say the history is going to store in the memory. So this is what I can call it as previous history. This is the simple circuit which we can define as sequential circuit. Okay, generally if you take the basic examples, what are comes under combination circuits means, we have various kind of arithmetic circuits are there. Arithmetic circuits like adder, subtractor, multiplier, those are all will comes under combination circuit. If you would like to convert one code to another code, those also will comes under combination circuits. Okay, uh, something like encoders and decoders, right? We'll go through all this one by one later part. Encoders and decoders also comes under combination circuits, and the other kind of combination circuits are multiplexers and demultiplexers. These are the some of the examples for combinational circuits. If you look into the examples of sequential circuits, registers are one kind of examples where it contains the internal memory. Flip-flops are another kind of example for sequential circuits. Counters are there. All these are we are going to see. Okay, fine. See, basically, guys, which one is faster? Combination circuit is faster because these are not depend upon any previous input or any previous history. Whereas coming to sequence circuits, these are somewhat slow compared to combination circuit because those are depend upon previous history. Okay, and in terms of design point of view also, combinational circuits are very easy to design because it doesn't contain any extra memory elements, all those things, right? Because as there is no memory elements existed, it is easy for us to design. But coming to sequential circuits, it is somewhat complex to design. Okay, so this is what the difference between combination circuits and sequential circuits. Okay, fine. So now what I will do now, I will try to take one of the combination circuit like arithmetic circuits. Arithmetic circuits. These arithmetic circuits are comes under combination circuits only, right? That's why I have taken the example. Okay, so one of the arithmetic circuits example is adders. Adders means you are going to have any data, that data it is going to be performed. Say for example, if I try to take a 2-bit number, like one bit is 0, another bit is 1. What is the result you are going to get? You are going to get as 1, right? Meaning that if you are going to have the two inputs A and B, when you are trying to perform the sum operation, you are going to get 1. And what about the carry? Carry is 0. Carry is 0. Similarly, when you are going to have the input 1 and 0, output will be, sum will be 1, carry will be 0. When you are going to have 1 and 1 as input, sum will be 0, carry will be 1, right? I hope you know how to get this one, right? When the inputs are 0 and 0, sum will be 0, carry also will be 0. Okay, so this kind of operation I can call it as half order sum. Adding only I can call as half adders, right? So here, so why I am going to call as half adders means these kind of adders are going to add only 2 bits, 2 bits. But in the real world, if you look into the real world, is it really contains only 2 bits to add? No. See, for example, if I am going to take 1 and 1, 0 and 1. If I am trying to add 1 and 1, you are going to get 1 0. And how many bits you need to add for the next time? 3 bits you need to add, right? 3 bits to unit to add, right? But you cannot able to add with the help of this logic. With help of this logic, you cannot able to add, right? That's why I am going to call it as half adders, meaning that half adders are meant for to add 2 bits only. Okay, fine. So guys, when you are going to have a truth table, can you able to derive the expression for this one? Yes. See, basically here the thing is, your requirement is you are going to have two inputs A and one input is B, and there is a circuit called half adder circuit. This half adder circuit is going to produce sum as output and carry as also an output, right? This is what your requirement, meaning that this circuit is going to take two inputs and it has to produce the correct sum and carry. How we are going to do that, right? So based on the given requirement, see, basically what you are going to do, this is the requirement given by the client, the requirement, or I can say that specifications are given by the client. Once these specifications are given, I try to analyze it, then I try to construct the truth table for it, right? So that is the reason I constructed here truth table. Once I tries to construct the truth table, can I able to construct boolean function? Yes. How we are going to construct the boolean function? Basically, it's like a kind of uh, XR operation. If you are able to observe, right? Uh, if you are able to, I can directly write one way is this one I can call it as a bar b. I'm trying to take one, and this one I can call it as a b bar. See, finally the expression is a bar b plus a b bar. Or what is the another way I have explained? I have explained in the form of K map, right? Two variable K map. If you take a b 0 0 0 1, see this is 0 0 1 0 1, 0 0 0 1 is 1, 1 0 is 1, right? So you can able to solve independently only. So this represents a bar b, and this represents a b bar. So if you are going to combine, again you are going to get the same expression. Indirectly I am saying that this is XOR operation. XOR operation. XOR operation is for what? Sum. To get the sum, we can able to perform the XOR operation. What about the carry? When you are going to get the carry, when both inputs are 1 and 1, then you are going to get the carry, right? So if you would like to solve it, what you can do? So this is for sum and it is for carry. AB, when you are going to have 1 and 1, then only that, right? If you are able to solve it, you are going to get AB. So AB is meant for carry, so which is like act as a AND operator. So this is exactly a sum and this is exactly a carry. Guys, we have got the boolean function. Now can we able to construct a circuit? Yes. So final operation is we can able to construct a circuit. How can we do that, right? So you know the inputs and the final function, right? I am going to have inputs A and B, A and B. So in order to get A bar B, what you can do? Can I make it complement A bar, and I can able to perform AND operation. I got A bar B, A bar B, and I am going to have A, A, and I need bar, right? This is going to produce A B bar. So this is A bar B and this is A B bar, right? Finally, you need to perform OR operation. You are going to get A B bar plus A bar B, which I can say that sum. So I can say that sum. What about AND? AND you are going to get from the same circuit, you will get A and you required B. This is what I can call it as carry. Right? Now this is the circuit which is meant for to perform half adder operation. Okay, guys, the same circuit. So this is what with respect to basic gates. Can we able to do with respect to the expression directly? Yes. See, A and B are the inputs I got. Those inputs directly I can able to use XOR gate because the expression yield into XOR. So this is sum. How we are going to get carry? By simply taking this one. Right? So this is half adder circuit. So if somebody try to ask for you to construct half adder circuit, what you are going to do? You need to first analyze it, then you need to draw the truth table, then you need to derive the boolean function, then you need to construct its circuit. You should not by heart that. Okay, fine. Similarly, for example, I want to perform 3-bit addition. How can you do that? that I will explain right now, right? So that concept I can call it as full adder. Means the drawback of half adder is you can able to perform addition of 2 bits only. So in order to perform addition of 3 bits, I can use full adder. Can I perform 4-bit addition using full adder? No, it couldn't possible. That is a drawback of full adder, right? So you cannot able to perform 4-bit addition using full adder, single full adder. Okay, fine. So how can you do that? So basically the requirement is here what you are going to have. You are going to have 3 inputs. One is A, another one is B. This input I am going to give to a circuit. I am trying to say that the circuit is full adder. It needs to generate sum and it needs to generate a carry, and along with these two inputs basically you are going to have one more input. I can say that z, meaning that some extra input. So how many inputs we are trying to pass here? 3 inputs we are trying to pass. Okay, so instead of taking the extra other meaning terminology, I can say here mm, C only. Okay, A, B, C are the input, right? So if you are going to have 3 inputs A, B, C, what are the possibilities? Triple zero, 001, 010, 011, 100, 101, 110, triple one, right? Hmm. Right? So once the requirement given, you have to draw the truth table, right? So now how we are going to get the sum logic, how we are going to get the sum output, right? We have done many kind of operations on the sum and carry, right? So 0 and 0 is 0, 0 plus 0 is 0, carry also 0, carry also 0, right? 0 and 0 is 0, 0 and 1 is 1, carry is 0, 0 1 0. So I hope you know, so sum is 1, carry is 0, right? When you are going to have 0 1 1 as input, 0 and 1 is 1, 1 and 1 is sum is 0, carry is 1, 100, sum is 1, carry is 0, 101, sum is 0, carry is 1, 110, when you are going to have 110, sum is 0, carry is 1. Okay, and when you are going to have triple one, 1 plus 1 is 0 and carry is 1. For that you are going to add 1, you are going to get sum 1 and carry 1. So once we construct a truth table, you can able to derive the expression. You can able to derive the expression, right? So deriving the expression means you are trying to select all the min terms for the sum, right? So in order to get the sum expression, you can able to write all the ones. So it will be like this, right? So it will be like a bar, b bar, c, or a bar, b, c bar, or a, b bar, c bar, or a, b, c, a, b, c. Similarly, to generate a carry for the expression for the full adder, we can able to select these all, right? To select this one, you need to have a bar, b, c, plus this one is a, b bar, c, and this one is a, b, c bar, and this one is a, b, c. Okay, fine. Now with this expression, can we able to construct the circuit for this or not? Yes, we can able to construct this one easily. Okay, so we are going to have the inputs. We are going to have the inputs A and B and C. So basically, you can construct with the help of 2 input AND gate if required, or 3 input AND gate if required. So depending upon the requirement, or depending upon the requirement, or depending upon the question, you can able to solve it directly. I hope you know, right? Because this is in the form of AND OR gate. under gate, right? Once it is in the form of under gate, you can able to construct in the form of NAND nets also. Okay, fine. See, my requirement is I don't want to solve it in the form of basic gates. Basic gates. I want to simplify this expression. I want to simplify this, right? The same expression can I write like this? Sum of this is what this all the terms, right? Canonical forms can I write because everything in the form of standard sum of the products. Yes, I can write like 1, 2, 4, and 7. Sum of 1, 2, 4, and 7. And this I can write it as sum of 3, 5, 6, 7. So that I can able to simplify it easily, right? Yes. So for this sum, I am trying to draw K map for this. I am going to take A, B, C. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So 1 and 2, this is 4 and 7. 4 and 7, right? So all the remaining are zeros. 0, right? So this is for some K map, right? How we are going to solve this one, right? Is there any chance to form subcubes of size 2? It couldn't possible because all are not adjacent. So you have to take out everything individually, right? So if you are going to take this one indirectly, I can solve this. I can say it as A XOR B XOR sim. If you are going to simplify this one, okay, fine. Similarly, if you take the K map for carry, it will look like this: A B C 0 0 0 1 1 1 1 0 0 1, and 3 will be this one, 5 6 7. So how we are going to simplify this one? I can take out these two and these two and these two, right? So for this the carry will be if you are able to solve it, you will get xz plus xy plus yz, xz plus xy plus yz, right? So now which one is better? Is constructing this kind of circuits better, or these circuits are better, right? So constructing the circuit in this form is better because it is going to take less number of gates compared to that, right? Okay, fine. So here if you are able to construct the circuit, if you are able to construct the circuit for some, how we are going to do that? I am going to have the A and B as inputs. I am trying to take one XOR. You are going to get A XOR B. And for this output, I am going to add one more input called C, right? So this I need to give. I need to give, right? Finally, we are going to get A XOR B XOR C. So this I can say that sum. Okay, fine. What about the carry? Carry, you can able to simply perform. Uh, See, this one is AB. So I can write, I can solve it as, right? For example, if you try to take out this one, try to take this one. A is common, and on the x-axis C is common. So I can take it as AC. If I take this one, take this one. A is on y-axis, and B is on x-axis. And if you take this one, you can mark it as BC. Mark it as BC, right? Yes. right? This is the expression. So for this, you can simplify it. You can simplify to the circuit, but uh, the thing is, whatever the way that you are trying to construct, that is correct. So for example, I am trying to do that. AC, right? uh, A as input, A as input, you are going to get C also output, right? I am trying to perform AND operation. Similarly, for the same uh, A, for the same A, and there will be B. There will be B, right? For this one I got AC, for this one I got AB, and I need to have BC. I think this is B, and C I need to get, right? So diagram may not look clean, so don't worry. So I got C. Now with the help of OR gate, 3 input OR gate, I can able to combine. So you are going to get AC plus AB plus BC. This is what the circuit for full ladder. Full ladder, guys. But if you are able to observe, if you are able to observe, I can able to simplify this expression, right? See, observe. Uh, if I take the carry expression, the carry expression, what is the carry expression here? A bar BC, right? That is summation of 3 5 6 7. If you take this one, this is A bar BC, and how we are going to get 5? A B bar C, and 6 means what? A B C bar. 7 is A B C. Okay, fine. Now if you are trying to simplify this expression, I am trying to take some common terms between these two. Between these two, try to observe. I am trying to take out C as a common. You are going to get A bar B plus AB bar, and from these both two, I will get take out the common as AB. Then you are going to get, right? So if you are able to observe, I am going to write AB plus C into, I can write it as A XOR B, XOR B. Okay, this is what the carry. And what about the sum? Sum is as usual, like XOR gate, some 3 XOR gate, right? So I will try to redraw the structure. There exists A as input and B as input. I have A XOR B, XOR B. For this, I need to get A XOR B XOR C. So I am going to take certain input, the other input as C. So finally I am going to get A XOR B XOR C. Now this is sum. Okay. For this one, you need to have a carry, right? So carry means what? AB or C into A XOR B, right? First, can I do AB operation? Yes. I am trying to do AB operation. Okay. So this is what? AB. AB. Okay. After that, I need to perform C into A XOR B. So guys, you know A XOR B, A XOR B, A XOR B you got already. You got already. So I am going to take A XOR B, XOR B, that I am going to multiply it with C. You know C, right? Now here you got what? Here you got A XOR B into C, into C, right? For this, you need to take out OR gate, OR gate. Then you are going to get AB plus C into A XOR B. This is what I can call it as a carry. Guys, if you are able to observe this one, the reason why I have drawn the circuit, redrawn the circuit like this means, what do you mean by half adder? Half adder means it's a kind of XOR with AND gate. Simply XOR and AND gate, right? If you are able to observe this one, this part, I can call it as one half adder. Am I right? Yes. Similarly, if you are able to observe this part, I can call this also one kind of half adder, meaning that I can able to implement full adder with the help of two half adders along with one more OR gate. Basically, we can do with two half adders. That is what I can define with the help of this circuit diagram. Okay, so this is for today's class. Thank you.